All right, we've looked at stereochemistry, but there's another aspect of stereochemistry that we need to see. So this is a typical diene. Oops. My pen doesn't like to write up there. Okay. Not cool. This is a typical diene. And this is a typical dienophile. Note that the diene has an R group, and that R group is a donating group. And the dienophile has an R group, and that R group has a carbonyl. It's an electron-withdrawing group. When these two react, and they're going to react as shown, we are going to get this product. And the real question is, what is the stereochemistry of our two groups? Are these going to be cis or trans? And to do this, there's really not a great shortcut. We just have to draw everything out longhand. So if you're waiting for the shortcut at the end, there is not really a shortcut. So how do we do this? So to do this, I like to draw the diene and dienophile from a different perspective. So I kind of want to look at the diene from this perspective. So we're looking at the diene with our eye in front. Of course, these hydrogens are poking towards us. The N hydrogens are poking towards us. So I want to show them sticking in, coming out of the plane of the writing surface. Of course, on carbon 1 and 4, we also have additional groups. We have a methoxy group of carbon 1. It's kind of sticking away from us. And on carbon 4, we have a hydrogen that's kind of sticking out to the left. Now, that's the diene. Let's draw the dienophile. The diene and dienophile are going to react with each other. 5 and 6. Now we're also going to draw the dienophile flat. So we're going to have groups coming out towards us and groups kind of sticking away from us. Carbon 5, it doesn't matter because they're both hydrogens, so let's just fill them in. The real question is, what do we do on carbon 6? This ketone group can either come towards us or it's going to tuck back away from us. As it turns out, it tucks away from us. As an electron withdrawing group, it has a pi bond, that CO pi bond, and as it turns out, that pi bond of the carbonyl on the dienophile loves to sit underneath the pi bonds of the diene. That's a stabilizing effect. It's just a weird orbital effect. And as a result, when this cycloaddition occurs, push the electrons around, we get a product. Of course, it's a cyclohexene. Always get a cyclohexene out. I'm going to number these on the inside so the numbers stay away from our groups coming off the ring. When we determine the stereochemistry of our groups in the product, just look for all your wedges. Note that each carbon, 1, 4, 5, and 6, has one group that is wedged. Those groups end up being up on the stereocenter. So, in fact, let's go ahead and put our dashes and wedges in. What gets a wedge on carbon 5? A hydrogen. Hydrogen also gets a dash, doesn't really matter. Carbon 4 is the same thing, they're both hydrogens. Not really a mystery there. Now carbon 6, the wedge goes to the hydrogen and the dash goes to the ketone. Carbon number 1, the wedge goes to the hydrogen, and the methoxy gets the hashed bond. Now, this isn't the only product that we get. We also get the enantiomer. So here we've drawn this with our two R groups being cis, and we've chosen cis down. If we redrew this molecule and drew the enantiomer, which would be cis up, that would be the other product. However, we would not draw a trans product where one of these groups is up and one of the groups is down. We'll draw them either both up or both down. This effect of our group wanting to be tucked underneath the pi bond of the diene is called the endo effect. So sometimes when people talk about stereochemistry of Diels-Alder reactions, you'll hear the term endo effect thrown around. And that's a reference to the preference of the electron withdrawing group on the dienophile wanting to tuck underneath the diene pi system in the transition state.